Hi, welcome back. We've been talking about the practical applications to the Fourier series, and one of those applications is what's called filtering. Filtering allows us to accept or reject certain frequency components. Like in communications, if we want to accept 101 megahertz because that's the carrier frequency whose signal we want to listen to, and we want to reject all of the other frequencies that our antenna picks up, then we need to filter out those frequencies and allow the 101 megahertz signal to pass through. So let's take a look at filtering and how it applies to the Fourier series coefficients. Now, I have the results here from the previous video's example. If you did not watch that video, or if you didn't quite understand it, that's okay. This is the result of that video, and all you need to know is the result. So in the example, we have a linear time-invariant system whose frequency response, capital H, is 1 over 1 minus alpha e to the minus j omega, where alpha is a constant whose magnitude is less than 1. We put into that system cosine of pi over 2n, and we get out of that system 1 over the square root of 1 plus alpha squared times cosine of pi over 2n minus the inverse tangent of alpha. That's the result. And one of the things that we needed to come up with that was the fact that the output Fourier series coefficients were the input Fourier series coefficients multiplied by the frequency response evaluated at k omega 0. Okay, that was very important to this problem. Now, remember what the Fourier series coefficients are telling us. They say how much of each harmonic component we have. And so, if bk is the output, and the input Fourier series coefficients are getting scaled by capital H, then if we had a system whose capital H happened to be 0 for some harmonic frequencies, then those frequencies would not, or we would have 0 of that frequency at the output. You see, if capital H is 0 at some frequencies, then those frequencies are unable to get to the output. Thus, we call that filtering. And they don't have to be exactly 0. We can attenuate some frequencies, meaning maybe they pass through the system, but there's less of that harmonic component than at the input. Or we can amplify some frequencies, meaning there's more of that harmonic component than there was at the input. Now, let's come to this example where we have our frequency response is 1 over 1 minus alpha e to the minus j omega. What's important here is to realize that this is a complex function of omega, right? Because the j is there. So I might end up wanting to make a plot of this guy. Plots will be handy in a little bit. But because it's complex, I need 2 plots. Usually the magnitude and the phase. Another choice is the real part and the imaginary part. But the magnitude and the phase is going to be more convenient for us. So let me find the magnitude of this expression. So the magnitude of the numerator is 1, and then I need to figure out what the magnitude of the denominator is. Okay, and to do that, I'm going to express the denominator in rectangular form. So we're going to use Euler again. E to the minus j omega is cosine of minus omega plus j sine of minus omega. Okay, now let me work on that a little bit. Cosine is an even function, so I can just get rid of the minus omega like that. And sine is an odd function, so I can bring the minus outside. And when I distribute the minus alpha in, it becomes plus. like this. Now, in the denominator, I clearly have a real part, 1 minus alpha cosine omega, and I clearly have an imaginary part, alpha sine omega. So now I can use the Pythagorean theorem to find the magnitude of the denominator. That's 1 minus alpha cosine omega squared plus alpha squared sine squared, like that. I ran out of room there, but all of that should be in the radical. All right, so now if I FOIL that cosine term, I have 1 minus 2 alpha cosine of omega plus alpha squared cosine squared omega plus alpha squared sine squared omega, like this. And since sine squared plus cosine squared is 1, I have the following: alpha squared minus 2 alpha cosine omega plus 1. Okay? That's my final expression. That's the magnitude of the frequency response. Sometimes we call that the magnitude response. It's convenient to make a plot of that, so let me do this. So this is going to be omega. And you can pick a value of alpha. Alpha is a parameter. It has to have a magnitude of less than 1. But you can plot this on your calculator or whatever you want to do. Choose a value of alpha, and you'll see that it looks like this. Okay, and again, that's the magnitude response. And the height, the maximum there happens at the origin, and the height there is 1 over alpha. And the minimum here happens at pi. Okay, and minus pi. So we have something like this. And the maximum, again, it's periodic with period 2 pi. And so we have something that looks like this. Now, what's interesting here is that if I plug in pi over 2, so somewhere around here, what I get, so I'm going to do this in a different color so we make it clear. Here's pi over 2, and the height of that thing, if you work it out, right, if you plug in pi over 2 here, cosine of pi over 2 is 0, right? And then you have 1 over the square root of alpha squared plus 1. That's exactly this. So this has a height of the square root of 1 plus alpha squared, like that. So notice, when we put a cosine at this frequency, pi over 2, what ended up happening here was that the amplitude, which was 1, got scaled by the magnitude response. This is the magnitude response, evaluated at pi over 2, the frequency. Okay, take a second to really think about that. We put in pi over 2, so here's pi over 2. The magnitude response has a height of this, 1 over the square root of 1 plus alpha squared, and that's exactly what ended up multiplying our cosine, scaling our amplitude. That's not a coincidence. Okay, now let's go back to our frequency response. Okay, here it is again, 1 over 1 minus alpha e to the minus j omega. Let's find the phase. This thing only tells half the story. So the phase of that complex expression, the phase of 1 minus alpha e to the minus j omega, is equal to the phase of the numerator is 0 minus the phase of the denominator. Actually, let me back up. I want to express this in rectangular form again. So this is 1 minus alpha cosine omega plus j alpha sine omega. Okay, so I want the phase of this thing. So the phase of the numerator is 0 minus the phase of the denominator, and the phase of the denominator is the inverse tangent of the imaginary part over the real part. Like this. So, and of course, you don't have to write the 0, but that's the expression. So now you pick a value of alpha, whatever your parameter alpha is, maybe 1/2, and you can make a plot of this. So let's do that. Okay, so this is omega, and you don't need to know what this looks like off the top of your head, but it looks like something like this. It's kind of a skewed sine wave almost, and this has a height of alpha, I believe, minus alpha. And it happens that when you plug in pi over 2, you get a height here of minus the inverse tangent of alpha. And when you plug in minus pi over 2, it happens here that you get the inverse tangent of alpha. So what is that telling us? Well, it's no coincidence. That's what we get here, the output. So the phase we get is, actually, let me back up. This thing is called the phase response. So the phase that we get out at the output is the phase response evaluated at the frequency that we're putting in. And remember, the cosine has the first harmonic, pi over 2, and the negative first harmonic, minus pi over 2. And that's why we have the inverse tangent of alpha. So this frequency response is proving to be very important. And again, remember, the frequency response can be kind of partitioned into the magnitude response and the phase response. Now, so what good is this? Well, remember about that scaling constant. So that goes back to the magnitude response. If we were to scale this by something large, then that would be emphasizing the frequency. And if we were to scale this by something small, then that would be attenuating or de-emphasizing that frequency. So look at our magnitude response here at pi. Pi is a high frequency in discrete time. It's actually the highest frequency in discrete time. So if we were to put a frequency of pi into this system, then we would get something small out. That is, we wouldn't get a lot of that frequency out. However, if we put low frequencies in, like 0 or 2 pi or 4 pi, that's where this thing has a maximum. And so those frequencies are scaled by a large number, a relatively large number, and so the low frequencies are amplified. Thus, we could argue that this thing is what's called a low-pass filter. It's a type of low-pass filter, although it's not a very good one, which I will explain, well, right now, actually. So I'm going to delete this. Feel free to pause the video. Okay, so now we start to see how this thing is, again, this frequency response is filtering out frequencies or emphasizing other frequencies. So we have a couple filters that are very important to us. And really it's based on the magnitude response. So I'm going to just write, actually I'll write them both. I'll draw the phase response and the frequency and the magnitude response. So if we had a filter like this, where this we'll call omega C, C stands for cutoff. and this is a height of 1, and this is our magnitude response. Okay, and if the phase response were 0, so this is the phase response, if these two things hold, then this is what's called an ideal low-pass filter. Okay, let's try to understand why it's called a low-pass filter. If you put in frequencies less than some parameter, omega c, then those frequencies get scaled by exactly 1, meaning they pass perfectly through with no phase distortion at all. The phase remains unchanged. That's ideal. If you put in frequencies larger than omega c, then they get scaled by exactly 0, meaning they don't get out at all. So you will not see those frequencies at all. And it doesn't matter what the phase is at that point. So this is an ideal low-pass filter. Turns out you can't build such a thing, but you can approximate it. But we'll talk about that later. Now, that's one type of filter. Another type would be what's called a high-pass filter. And a high-pass filter has kind of just the opposite. Is the opposite situation, where we have a cutoff frequency, omega c, okay, this is omega axis here, and this is the magnitude response. And for frequencies less than omega c, they get attenuated perfectly, meaning they don't get through at all. And then for frequencies larger than omega c, they get scaled by 1, so they get through perfectly. They get through. So this would be a high-pass filter. And an ideal high-pass filter is one whose phase response is exactly 0. So this would be the phase of the frequency. So the phase response, so that the frequencies that do get passed through, they get through with no phase distortion. Okay, and we can have other things. We can have band pass filters, where maybe we don't want low, but we don't want high, and so we have a certain band that we want to pass through. Right? Something like this, where this would be the magnitude response. And actually, the phase response does not really matter too much, but ideally it would be 0. The phase would be 0 in this band. So low frequencies are getting attenuated perfectly. High frequencies are getting attenuated perfectly, but intermediate frequencies get passed through perfectly. They get scaled by 1. So this would be a bandpass filter. Okay. And the last one I want to mention, there are others, is an all-pass filter. Okay, and an all-pass filter has the magnitude response that is constant, like this, and it's 1. So all of the frequencies pass through perfectly. Why you would want such a filter is you would want to do something to the phase. You'd want to correct some sort of phase distortion. But without knowing the application, I don't want to draw the phase response because I don't know, it's application dependent. But for the magnitude, you want all of the frequencies to get through if you want an all-pass filter. Okay, so that's the idea behind filtering. Again, there are other types of filters, but these are the most common ones that you will see. Now, in the next video, I want to show you how we can start to build a low-pass filter using an RC circuit. So we'll draw on some concepts from circuits. If you don't remember circuits, that's okay. But we can actually start to build these things that have approximately these responses. So let's take a look in the next video.